Okay, so we're going to tackle lesson number 3 right now, start and finish. Lesson 3 is all about linear models. Models are just equations that arise from some hopefully realistic situation. That's what we're about to do here, starting on page 17. We'll begin with our daily summary. In this lesson, we solve word problems that involve linear equations, and we graph lines using intercepts. We also learn how to identify dependent and independent variables, as well as how to write an equation for one variable in terms of another. Some of the stuff today is probably going to look familiar to many of you, but there's a lot of vocabulary, and some of that vocabulary might be new. There is some reference here to My Math Lab. Remember, you can ignore anything in the packet that says My Math Lab. Okay, number 1 is a reminder. Do not use your calculator on any problem in the class packets unless the instructions tell you to do so. Almost everything this semester is going to be without the calculator, but when it's time to use it, it will be clearly written in the packet. All right, definition. A model is a mathematical description of a real-world situation. Suppose an individual works X hours at a salary of $15 per hour. X is the number of hours. $15 per hour is the salary. Part A, we're going to fill in the table of values showing the wages W in dollars earned for the number of hours worked X. And so you can see the first column here is X, which is number of hours worked. Might work 0 hours or 4 hours or 6 hours or 10. And then W over here is the wages earned in dollars. So if you work 0 hours, how many dollars do you earn? 0. Sad but true. If you work 4 hours, how do we calculate our overall wage? 4 times the $15, right? Okay, so 4 times 15, that's 60. And if we work 6 hours, how do we calculate? 6 times 15, right? 6 hours, $15 per hour. So 6 times 15, I think that's 90. And then finally, the last one, 10 hours at $15 an hour is 150 bucks. Great. Okay, so now what we're going to do in part B is plot the points from the table in part A and draw the line that connects those points. So I guess I didn't do a good job of labeling my axes here, but it's the same X, number of hours, and the same W, which is this vertical axis, which is the wages earned. So we're just going to plot some points. So the first one is at 0, 0 at the origin. Kind of having trouble seeing where the axis is on my page. Your copy looks, yeah, yours looks a little bit nicer than mine does. I think I'm in the right spot there. Okay, and then 4, 60, it's there, and then 690. So we're just plotting lots of points. And then 10, 150. I think it's there. All right, and so if you have a straight edge, go ahead and use it. Play connect the dots. Feel free to use my green folder. Oh, and make sure you sign in on the green folder. We do that every day. So just write down the, I prefer the time that you got here. So if you have a check mark, you can erase it and just put down the time that you got here on that green folder. We start at 10 o'clock, so maybe you got here a little bit early. And then we connect the dots with a line. I don't want to brag, but oftentimes my lines miss most of the points on the board. So that is like, that's going on the highlight reel, right? Again, this is why my YouTube playlist is blowing up, is high quality lines like that one right there. All right, part C, first brand new vocabulary for us. Write an equation for W, wages, in terms of X, number of hours. Write an equation for W in terms of X. There is a brand new phrase here, in terms of. It is precisely defined in math, and we are introducing it right now. When you see that phrase in terms of, it means write an equation of the form W equals some stuff with X's in it. Okay, so all of these dot, dot, dots is my informal way of saying there's X's floating around. There might be multiple X's floating around. The complicated thing is the thing with X's in it. But the important thing is that W is by itself in that equation. So when you see W in terms of, it means that W is by itself. So when I see W in terms of, the first thing I do is translate that in terms of to an equal sign. W equals W in terms of, and then we got to do the work on the right-hand side. Okay, let's give it a shot. W in terms of W equals. Okay, how did we calculate it? When it was 6 hours, what did we do to get the wages? Multiplied by 15. And when it was 4 hours, we multiplied that by 15. And if it's X hours, we multiply X by 15. 15X, okay? That's it. Okay, part D. For each increase of 1 hour, how much more does the individual earn? $15, right? Every time you increase by an hour, you earn $15 more. Does that hourly rate change or does it stay constant? It stays constant. It's just $15 per hour no matter what, right? And in fact, there's a word from your math history that says exactly that. Let me use a different color here. Yes? Yes. Yeah, 15 times X. Okay, so here we go. If you work 1 more hour, you earn $15 more. If you work 1 more hour, you earn $15 more. 1 more hour, $15 more. What word from your math past is that 15? Starts with an S. Slope. That is the slope. Yes? Every time you run 1 to the right, you have to rise 15. That is the slope. We'll talk about slope plenty in this class very soon. Not today, but it's something you've seen before, I think. Okay. And the fact that that stays constant is kind of the defining characteristic of a line. The fact that it's always $15 an hour is what makes it something that is straight. Whereas if you imagine, okay, it's 15 bucks an hour until you get up to say 10 hours, and then maybe you're working overtime. And hopefully we're getting like time and a half when we're working overtime. So maybe the hourly rate goes up to like 22 bucks after you get past 10. And so can you tell me what would happen to the rest of this line to the right? It'd be steeper, right? Like here you're earning 15 bucks an hour, but then all of a sudden you're earning $22 an hour, and it's not just a single line anymore. So again, kind of the defining characteristic of a line is that the rate of change is always the same. In this case, over 1 up 15. Okay. So that's kind of written here. For each additional hour worked, there's always an increase of $15. This is an example of a constant rate of change. This constant rate of change between two variables, in this case hours and wages, is what distinguishes linear models from other types of models. A quick detour. We're going to talk about graphs like this much later in the semester. Anybody know the name of that graph? That's a parabola. We'll talk about them. But you will notice that it is not a constant rate of change. You don't need to label this, but I'll just put a few points up here. 0, 0 is there. That's 1, 1. There's the equation y equals x squared. Next point, again, I can't quite see. I think it's here. That's 2, 4. And we'll do one more up here at 3, 9. So if I go, let's do this here. If I go 1 to the right, I need to go up 1. But in the next case, if I go 1 to the right, I need to go up 3. So I used to be at 1 and now I'm at 4. And to get from 4 to 9, how far up? I got to go up 5. So it's not like over 1 up 15, over 1 up 15, over 1 up 15. It's changing. It was over 1 up 1, then over 1 up 3, then over 1 up 5, even more. It's not a constant rate of change. It is something curvy, not straight. Okay. On the next page. Another vocabulary phrase right here, dependent and independent variables. Might be old, might be new for some of you. Since our wages depend on the number of hours we work, our wages depend on the number of hours we work, we call W the dependent variable and X the independent variable. Does that make sense? It's like you work a certain number of hours and therefore you earn a certain wage. It doesn't really go the other direction. It's not like you earn a certain wage and then you go out and work those hours, right? Clearly the number of hours dictates what your wages are. So that's why we define the wage to be the dependent variable. It depends on the number of hours. Okay, in some cases like this, it's pretty clear which one depends on the other. But there are going to be other scenarios where there isn't really a clear kind of like horse leading the cart relationship. And you could kind of make the case that, oh, the one variable kind of depends on the other or in the other direction. So again, it's a mathematically defined phrase. I will tell you that the variable that is by itself, I'll write our equation. W equals 15x is our equation. Even if I didn't know that this came from wages and hours, it is clear that W is a dependent variable. Whichever letter is by itself is defined to be the dependent variable. Whichever letter is by itself is defined to be the dependent variable. I've got this little cutesy mnemonic device. If it works for you, great. You guys remember Pirates of the Caribbean with Johnny Depp? Okay, so if you think of Johnny Depp stranded on an island by himself in that movie, the thing by itself is the dependent, thank you, the dependent variable, right? Johnny, it's a little bit of a stretch, Yep. But the dependent variable, the dependent variable is the one by itself. And you picture Johnny Depp as a buccaneer on an island by himself. So coming to these two equations here, R equals T over 121 and T equals 121R. Both equations are representing the same exact thing. And I don't even need to tell you what T and R represent. Can you write down, copy one of those equations that expresses T in terms of R? T in terms of R. Does that mean R is by itself or T is by itself? Okay, which one is it here? T equals, right?
It's kind of the same thing.
Yes, T depends on R is another synonym.
Yeah.
Great. Okay, let's fill in the blanks in part B based on this blue equation we've just written here. Since which letter is by itself in this blue equation? T is by itself, imagining on the island. In the equation we just wrote, that same T is the which variable? The dependent variable by itself. And therefore the other one must be the independent variable. So R is the independent variable. Okay, so we've got one more new short topic to tackle before we jump into the activity, but I think we're right around halfway, so everybody stand up. We're going to move here. All right, so number 3 says, let's fill in the table with the intercepts of the equation 3x plus 2y equals 12. So brand new equation. We're going to graph this equation 3x plus 2y equals 12. It turns out the graph is going to be a line. Much of what we do in these first like several weeks of the semester is going to be lines. And so what we're going to do is define this thing called the intercepts. So intercepts, I'm just going to draw a line, but then don't copy it. We'll get rid of it in a moment. So intercepts of that line are places where the line hits what? The x-axis and the y-axis, okay? And so for example, right over here, we've got the x-intercept, the place where the line hits the x-axis. And then over here, we've got the y-intercept, okay? Imagine we don't have that line at all, but we just have, by some miracle, those 2 points. Let's say we do some calculation to get those 2 points. How many lines hit those 2 points? Just one. And so if we can find those 2 points, we just play connect the dots and we've got the entire line, okay? So that's what we're after. And these, again, are what we're calling the intercepts. Can you tell me, just sort of estimate, what are the coordinates of this point up here? 0, 4. And what if it happened that the y-intercept was up here? That's 0, 9, and maybe the y-intercept is down here. 0, negative 5. What's the same no matter where the y-intercept is? 0 for what? The x, right? Doesn't matter where the y-intercept is. If you live on the y-axis, your x coordinate is 0. And so that's how we calculate the y-intercept, is we let the x equal 0, right? It's not just sort of wait and see what happens. It is like an assertive. We are going to force x to equal 0, and then we're going to calculate what the y has to be. So let's give it a shot. We are going to write in here. We're going to let x equal 0, and we're going to write down the equation that results. So instead of 3x, we have 3 times 0, and then I'm copying everything else there. Plus 2y equals 12, right? We let x equal 0, and we will find the y. Okay, so 3 times 0 is 0. Oops. And then 0 plus 2y, that's just 2y. And then we divide by 2, and we get y equals 6. So the y-intercept is at 6, okay? So,
Right, 0. So it'd be 6 under the y and then 0, 6.
yeah, it is exactly that. I'm going to make a common mistake before we get to your right answer right there. All right, that was so much fun. Let's play the same game, but find the x-intercept. What can you say about the coordinates of every one of these points on the x-axis? The y is 0, right? The y is 0 at every one of those points. So that is how we begin. We let the y equal 0. But we go back to the original equation. It's rewritten here. 3x plus 2y equals 12. So we're copying everything except for the y, which gets replaced with a 0. Okay, let's see if we can solve this. We'll do this a little bit quicker. 2 times nothing is nothing, plus nothing doesn't contribute, so I'm just going to write 3x equals 12, and therefore x equals 4. Okay, so putting it all together, I see that y is equal to 6 and x is equal to 4, and I know how to write that. That's really 4 comma 6, right? X is 4, y is 6, 4, 6, bam. 4, 6. I'm hoping we didn't copy too much of that because it's all wrong. What did we do that was wrong? Yeah, why? Intercepts are supposed to live on the axes, but 4, 6 is floating up there in the first quadrant. What happened? We have to use the zeros. The 4 only came from letting the y equal 0. The 4 has nothing to do with the 6, right? And so this is what Teresa was after before. Let's start up here. We let x equal 0 and we calculated y equals 6. X is 0, y is 6. That is a single point right there, 0, comma 6. 0, comma 6, right there. And then completely independent from that point, we let y equal 0 and we got x equals 4. So x is 4 and y is 0. And what are the coordinates there? 4, 0. And we can plot that point. By doing bogus math. I combined.
I looked away for a second.
No. You're gonna, don't assume that I'm doing it right. Yeah, 4 and 6 are not to be combined. Yeah, Teresa.
In the left upper quadrant, quadrant 2,
Yeah.
I believe.
Yeah.
Is that 0, 6?
A 0, 6 is this purple point. I just labeled it out there. Yeah. Okay, so we've got our 2 points. Again, I made a mistake here, but you can see where 4, 6 came from. It was like a hybrid of the 2 intercepts, right? Like there's your 4 and there's your 6, but they're 2 separate points and you can't smush them together into one. So I think it's a really good idea to do what Teresa suggested, is that as soon as you get the number like 6, you immediately write down, okay, it came from a 0. It's not just an independent 6 waiting for a partner. The partner was 0 from the start. Okay, so we get rid of that, and we get rid of all of this, and then we've got our 2 legitimate intercepts, and then we play connect the dots, and we've got our line, right? Okay, so the way that we just graphed that line is called the intercept method of graphing the line. You find the 2 intercepts, and then you connect the dots. I think that the easiest way to graph lines of the form ax plus by equals c is just what we did up there. I know that some people, when they see the equation of a line, feel compelled to solve for which letter? Is it x? I've seen this so many times where students will solve this for y. You don't need to write this, but solving for y is no mean feat. Subtract the 3x from both sides. 12 minus 3x. And then how do we solve for y? So we divide everything by 2. So we go 12 minus 3x all divided by 2. And that's kind of messy. And so if you really want it to look like an mx plus b thing, you have to take that 2 and put it underneath both terms. It's a 12 over 2 and then minus a 3x over 2. Okay, sure, it looks like y equals mx plus b, but it's a lot of work to get to that. You can tell the slope, you can tell the y-intercept. We're going to do mx plus b stuff very soon officially, but I know a lot of students feel like obligated. I got to solve for y. Any line, I have to get it to look like y equals mx plus b. You can, but again, I don't think that's the easiest way to graph this line. I think what we just did here is the easiest way because plugging zeros in is really simple. So intercepts are useful. Okay, I think that is good. Here's our conclusion. To find an intercept, you let the other variable equal 0. How did we find the y-intercept? How did we start? X equals 0, the other. You want to find the y, you let the other variable equal 0. How did we find the x-intercept? We let the y equal 0. Okay? All right, activity starts a couple of pages away. Let's see how far we can get.